Hello, welcome students to the 32nd lecture on particle physics. In the last lecture, we were discussing formation of white dwarf stars, and what I had told you that the death phase of the star depends upon the mass of the core of a star, and all these stars are not of the same kind. There are stars which are much massive than our sun. There are also stars which are very less massive than our sun. Now, if the mass of the sun we are talking about is such that we have hydrogen fusion and helium fusion, and that ultimately gives rise to carbon and oxygen nuclei in the core of the sun, then what we talked about, that this will happen when the star will become red giant, and then because of the lack in the fuel, the temperature is not sufficient enough, will be sufficient enough to have the fusion of carbon or oxygen nuclei. Therefore, to have that fusion, the core of the star will start shrinking tremendously, and the radiation will come out very fast, that we have seen around 20 kilometers per second, 30 kilometers per second, and this will expand the outer envelope of the star. And since this outer envelope will ultimately, you can think of that, since there is a strong gravitational pull as the core of that, from where these radiations are originating, therefore they are moving apart because of the radiations coming out from it and taking the matter further away. But these radiations are sufficient enough to keep this place, the surroundings, very hot, and this we call it as planetary nebulae. It is not a planet, it is not a nebula, this is just the remnant or the outer envelope of the original star, and then the core that is left with is a white dwarf, and this white dwarf will slowly again cool, and ultimately it will also become a black dwarf. Let us start from this place. Therefore, what we are talking about, white dwarfs are approximately the size of the Earth, yet they contain much of the material of the original star. The density of the material of white dwarf is extremely large. It is about million grams per centimeter cube. If such material existed on Earth, 1 centimeter of cube would weigh a ton. Therefore, you can think of the mass of these core of the stars, though they have become very small, but since they are very dense, therefore the mass that is inside that of white dwarf is really very large. Now, white dwarf must have masses less than 1.4 mass of the sun. This is what I had told you, that between 0.4 to 1.4 mass of the sun, these stars will become the mass of the core of the star. If it lies between these two values, it will become a white dwarf, and this is known by the name Chandrasekhar limit. Now, what happens when we are talking about the shrinking of the core? Then there is an important quantum mechanical concept that is quite relevant here, and that is known as degeneracy of the electrons, and that is from, you can understand, if you understand the Pauli's exclusion principle, that no two identical particles can have all the quantum numbers same. Therefore, what is happening if we talk about regular gas, many energy levels are available, particles are free to move about and change energy levels. But if you talk about degenerate gas, all lower energy levels are filled with two particles, each with opposite spins. Particles are locked in a place. Therefore, if you have your core is shrinking, and matter, as I have told you, in all these stars you have matter and electrons are there. Therefore, what is happening that you have the degenerate levels where electrons are filled, and therefore when you have the filled electrons, therefore in that case you cannot further shrink the material. Now, what is the other concept is type 1a supernovae. What is type 1a supernova? It occurs in binary systems, that means two stars orbiting one another, in which one of these stars is a white dwarf star. Now, what happens when you are talking about a white dwarf star and you have another star? Then as you can see, the gravitational pull here, as I have told you, is really large. Now, if the gravitational force is really large, while this is a star which is huge in size, now the gravitational interaction between the core of this star, which is the parent one, is not strong enough in comparison to the gravitational pull of this white dwarf star that is attracting the outside material of the companion star. Therefore, what will happen? That slowly it will suck the matter from the atmosphere of the associated binary star, and as it will suck the material, slowly its mass will further increase, and a time will come when a huge explosion will take place and it will give out all the matter that was associated with this companion stars. So therefore, mass of white dwarf gradually increases and reaches to a limit where the whole thing goes off in one mammoth explosion known as thermonuclear runaway. Now let us come to the carbon and oxygen burning in massive red giant stars. Now what I had told you, that in low mass stars you have PP burning, and we saw that we have a beryllium, HEP neutrinos, beryllium neutrinos and all that. But here what is dominant reaction? This is the CNO cycle that we have discussed in the last class. And first we are talking about all those stars which are having masses 4 times the mass of the sun and less than the 8 mass of the sun. At the same time, in other words, we will say that we will talk about those stars whose core mass is more than 1.4 mass of the sun and less than 3 mass of the sun. Now, in massive red giants, the temperature and pressure are high enough to cause carbon to fuse into heavier elements like oxygen and silicon. Therefore, in the case of sun, the matter was not enough to have carbon fusion or oxygen fusion, but here we are talking about massive stars where the infalling matter are so much large in number that when they are falling, they are imparting their kinetic energy as the form of thermal energy to this system, and this system is gradually contracting and temperature of this system is gradually rising. Though part of that radiation will also come out, but at the same time radiation will also be trapped to increase the temperature of this core. At still higher temperature, silicon may fuse to form even heavier elements like iron and nickel. And that will be the full stop, because what we have seen, that mass per nucleon is least in the case of one of the isotope of iron, or the binding energy per nucleon is maximum for one of the isotope of the iron, and that is around 8.8 MeV. Therefore, you cannot have fission or fusion of this nuclei. Therefore, the important point is that when we are talking about oxygen fusion or carbon fusion, we can achieve up to silicon fusion. And ultimately, the object that we will have is iron. Now once we have iron inside the core, say this is the core, but still there is a shell. It is like onion like structure, because this outer part of this matter is hot enough to have still the silicon fusion, and the outer part of the other one, the third layer that we talk about, is hot enough to have oxygen fusion, and then outer part of that is hot enough to have helium fusion, and then the outermost part is hot enough to have hydrogen fusion. Therefore, what we are seeing is that all the matter that those are there are participating in this fusion reaction. The core is hot enough to have silicon fusion, then you have oxygen fusion, then you have carbon fusion, then you have helium fusion, and finally you have hydrogen fusion. That is why I am telling you that if the star is massive enough, the lifetime gradually decreases, and this is what is happening here also. Therefore, what you are seeing is the shell of onion like shell, where you have iron, then you have a silicon, then you have oxygen bonding taking place, then you have carbon bonding, then you have helium bonding, and the outermost layer you have hydrogen bonding. Therefore, the important point is that this hydrogen to helium bonding in such massive stars, that means such stars will remain in the main sequence for millions of years. Our sun will be there for 9 billion years, but for massive stars where this cooking is taking place with a much faster rate, the hydrogen fusion will be there for 1 million years. Then helium to carbon fusion will be there for 10 power 5 years. Oxygen to silicon will be there for 6 months. Silicon to iron will be there for 1 day, and then there will be core collapse in fraction of a second. Then what we are talking about, that we have a matter, huge amount of matter in the star's core, where we have hydrogen bonding, helium bonding, carbon bonding, oxygen bonding, and here silicon bonding, and ultimately iron is getting formed. Now you cannot have fusion of iron, but radiations are still building up. And what is happening? The star starts collapsing due to disintegration of nuclei of iron group via the reaction that the photon is disintegrating this iron to alpha particles, neutron, and consumes 124 MeV of energy. Therefore, what you are seeing, that suddenly neutrons starts building up. Neutrons we are getting neutrons because of the photodisintegration of the iron nuclei. And this is an interesting case, that we had already electron and proton inside the core, but at the same time, because of the photodisintegration of iron, we are getting neutrons. And then since we had electron and proton and the core is collapsing, therefore electron capture by the proton also starts taking place. And when the electron capture by the proton starts taking place, you have neutrons and neutrinos. This electron capture will also take place with the nuclei, and then you have some other nuclei and neutrinos will come out. Now initially, when the density is relatively less, these neutrinos are weakly interacting particle, they will come out. But as the star's core is further collapsing to have that, to counter that imbalance, then what is happening? Your electron is getting captured by proton, electron is getting captured by nuclei, you have neutrons and neutrinos are getting produced, which are initially coming out. But you have gradually, you are building up a stiff core, a very hard shell core, and then gradually as you are moving out, the outer part is less denser in comparison to this hard shell core. But still what is happening now, since neutrons are getting produced, initially these neutrons will also start collapsing, coming closer and closer to each other. But here, like in the case of white dwarf, we had electron degeneracy. Here neutron degeneracy will come into play. Therefore neutrons will start filling up the lowest state, and when you have all these states, lowest state filled up, this neutron, this place, the inside core will become so hard that further collapse will not be possible. And when this will happen, the neutrinos which were initially able to go out, now the density has become large enough that neutrinos are also getting trapped inside this star's environment. And at the same time, outside matter of this star is still falling onto this shell. Therefore, what happens when these stars outside material, which are in huge amount, are still falling because of the gravitational collapse, it is imparting energy to this hard shell, and since you cannot further shrink it, therefore what will happen? They will bounce back, and when they will, it is something like sea waves striking the shore, and then it's bouncing back and making lots of noise, lots of energy are coming out. Similarly here also, when the outside part of that star that is falling and it is striking this hardest core of the star, they are bouncing back, and when they are bouncing back, they are producing shock waves, and when these shock waves travel, they explode the environment of these stars, and when they are when they do that, then huge amount of energy gets, this shock wave is imparting huge amount of energy to blow out the outer envelope of the star, and these neutrinos which were getting trapped, they will start coming out. Therefore, this is what we call by the name supernova explosion. This is the implosion of the star and the explosion of the outer envelope, which releases huge amount of neutrinos, that is around 10 power 57 neutrinos. They come out in a few seconds of time and they get dispersed all around the universe. And this was first observed in 1987, which the neutrinos which we call by the name supernova 1987A. Now let us try to look at it. I am telling you that gradually a density inside the core reaches to 10 power 12 gram per centimeter cube, in which typical nuclei having masses A 80 to 100 in mass number with 50 neutrons are produced. Then the neutrinos, when this happens, the neutrinos which were coming initially, they are unable to come out. The collapsing star finally reaches to a density which is around 10 power 14 gram per centimeter cube, where the core becomes stiff enough, and we have why? Because we have reached to neutron degeneracy, and this neutron degeneracy comes into play. Therefore, like we have white dwarf, we have electron degeneracy. Here electron capture is taking place by the proton and the nuclei. We have the neutrons, and then shrinking of the core give rise to neutron degeneracy. Now, but in the case of very massive stars, like whose masses are more than 8 mass of the sun, or the core mass is 1.3 times mass of the sun, this neutron degeneracy also breaks, and then there is no control on the falling back of the matter, and there a black hole is formed. Now therefore what we are talking about, an iron core and this the outer part of this massive star. Now outer layers begin to collapse into inner core. The violent process leaves a contained shock waves. The matter of infalling layers compress and merge, triggering a blast of neutrinos to be released. Now convection results in standing accretion shock instability. The shock wave is released carrying the matter away in the blast, and the core is now a neutron star. This is how a neutron star is formed. Now here we are showing the Crab Nebula associated with 1054 supernovae. A tremendous explosion sends the rest of the star blasting away from the core at velocities up to 30,000 kilometers per second. A supernova has occurred. The shock wave produced by a supernova sweeps up an expanding shell of gas and dust from the interstellar matter and is observed as a supernova remnant. Therefore, this is like you have planetary nebula. Here we are talking about a supernova remnant. Therefore, what is a supernova explosion? This is the implosion of the star and the explosion of the outer envelope. And then the core of the star that is left with is what we call by the name neutron stars. And again, if you can recall from angular momentum conservation, since L has to be conserved, now this core was shrinking and it is becoming small enough that you may see that moment of inertia is decreasing. And that means to conserve angular momentum, angular velocity should increase, and that means this neutron star should revolve at the much faster rate. Therefore, what is a neutron star? The mass of the neutron star is about 1.5 mass of the sun. This is what I have told you, that this star has typically 1.4 mass of the sun to 3 mass of the sun. The diameter of neutron star is about 20 kilometers. As if you can recall, the sun's diameter is around 1400,000 kilometers. Roughly, it is 1.4 million kilometers, while the neutron star's size is only about 20 kilometers. But remember, they were very massive objects, much massive than sun, and therefore the density here will be much larger. And the neutron stars have very huge density, 10 power 15 gram per centimeter cube. While you recall, the sun's density is only 100 gram per centimeter cube. You can imagine how dense this medium is. Therefore, if you talk about a matchbox containing neutron star matter, that will weigh around 3 billion tons, or a mass of a cube with edges of about 800 meters of Earth. The surface temperature of a neutron star is around 600,000 Kelvin. The magnetic fields are between 10 power 8 to 10 power 15 times stronger as that of the Earth. This is what I was talking about, that to conserve angular momentum, the angular velocity increases, and this was first observed by the rotating neutron stars, and the observations were made for the beam of radiations. Those are coming out by Penzias and Wilsers, and these are called pulsars. Therefore, pulsars are nothing but pulsating stars, and they are nothing but the neutron stars which are rotating and giving rise to radiations which are coming out, which was for the first time observed by Penzias and Wilson. Now the important catch, why we talked about all this, because what I had told you, that neutrinos were initially getting trapped, and then this, when supernova explosion took place, the energy was carried by these neutrinos and they moved outward and almost 10 power 56 neutrinos are released typically in a supernova explosion, which comes out in a few seconds of time. And that is what we are going to discuss. Now, what I'm telling you, that 10 power 60 MeV of energy comes out, and energy carriers are neutrinos, almost 10 power 59 neutrinos of all flavors, nu e, nu e bar, nu mu bar, nu tau bar. While remember, when nuclear fusion in the star was taking place, it was all nu e type neutrinos, electron type neutrinos. There was no other flavor. But when you are talking about the trap of these neutrinos, these trapped really resulted in the interaction, in the scattering, and because of that, other flavors also got produced, and they were equal in numbers. Therefore, you had nu e bar, nu mu bar, nu tau bar. But the important point is, all of them are not carrying the same amount of energy. Why? Because if we talk about the matter inside that star, it is still electron, proton and neutron. And electron type neutrino, that we will discuss also in one of the classes, will interact with this matter via W exchange as well as neutral current exchange. While muon type neutrino and tauon type neutrino or anti-neutrino that you talk about will only interact through neutral current interaction. As you can remember, we talked about nu e lepton conservation at the vortices. Therefore, the important point is that electron type neutrino will interact through charge current as well as neutral current, while nu mu, nu tau will only interact via neutral current interaction. And therefore, the chances of losing energy by nu mu and nu tau type of neutrinos will be much smaller than nu e type of neutrinos. And that is why the average energy carried by nu e type is typically 10 MeVs, while average energy carried by nu mu and nu tau type neutrinos is around, in the simulation it has been shown that it is around 16 MeV. And this is because of this reason. There are all 6 type of neutrinos, 3 neutrinos, 3 anti-neutrinos, equal in number. But when this burst is taking place and they are coming out from there, they have the interaction with the surrounding matter, and these matter are nothing but electron, proton and neutron, and nu e will interact more in comparison to the other 2 flavors. And when you talk about anti-neutrinos, nu e bar will interact more in comparison to nu mu bar and nu tau bar. But if you compare nu e and nu e bar, then nu e will interact more than nu e bar, because nu e will have interaction with the electron also, while nu e bar cannot have a direct interaction with the electron. Nu e bar will interact with proton or neutron. Therefore, nu e bar has the handicap that it will interact with proton and neutron, while nu e will interact with electron also, while nu mu and nu tau, there the temperature is not enough to have the creation of muon or tauon, because muon is a particle which has a mass of 105 MeV, and tauon is a particle which has a mass of 1.7 GeV. While here we are talking about the typical energy carried by electron type neutrinos to be 10 MeV, and typical energy carried by tauon type neutrino or muon type neutrino to be 16 MeV. Yet therefore, you cannot have charge current interaction. You can have only neutral current interaction for nu mu and nu tau. And that is why they will carry more energy. But there is an important catch, and the catch is that though neutrinos are coming out, they are going to give us information about supernova explosion, that somewhere in space supernova has occurred. Otherwise, there is no direct information that we can get that whether somewhere supernova has occurred or not. These neutrinos, they will reach to us from some direction, where in the detector you will have suddenly a huge amount of neutrinos detection. You can say that from where this has originated, you can guess that they might have come from the supernova explosion. And since from the intensity, you can also tell us that how far that supernova explosion that has taken place is from the detector place. Therefore, this is an important point which one has to consider. The other important point, and that is really subtle in concept, is that when the neutrons were getting produced, initially they were getting trapped. We had the neutron degeneracy. Now it is something like when the supernova explosion took place and the outer envelope got burst and all the particles start coming out with the, it is something like when you have very heavy wind, then that will take all the leaves, the papers, it will also take away heavier things. Similarly here also, when this huge amount of neutrinos are coming out, they will take away along them some of the neutron, and these neutron will start coming out. But mind it, this neutron, when they start coming out from there, neutron get captured by the other nuclei, and this is the place where you have the formation of heavier elements in the star's environment. Therefore, the important point is you had up to iron because of the nuclear fusion reaction, but iron onwards is because of the neutron capture by the nuclei. Now it depends upon how massive that star is, because we are talking about stars having masses more than 4 mass of the sun and less than 8 mass of the sun or something like that. And we are talking about the scenario where neutrons flux are coming out. What is flux? Number of neutrons coming out per unit area per unit time because of that supernovae explosion. Now there are two positions or two circumstances when you have rapid neutron capture or where you can have slow neutron capture. Now this refers to how much is the mass of that star is. That means if it is really massive, you have more neutrons and those neutrons will come out in huge numbers, while if you have relatively lesser mass stars, then you have less neutrons and those neutrons will be smaller in numbers, and then there we are talking about slow neutron captures. Therefore, you have fast neutron capture, that is known by the name R process nucleosynthesis, and slow neutron capture, that is known by the name slow S process nucleosynthesis. Therefore, let me first summarize what are supernova neutrinos. Neutrinos make supernova explode. Neutrinos push the shock waves and blow up the star. Total number of neutrinos that reach Earth if a supernova explosion takes place in large Magellanic Cloud, which is 50 kiloparsec away from here, will be around 10 power 10 neutrinos per centimeter squared. That means per centimeter square on Earth, we will have 20 billion neutrinos if supernova explosion happens to be in the Large Magellanic Cloud. Supernova 1987A neutrinos were detected at Kamiokande, IMB and other places. Now we are going to talk about more on supernova neutrinos in the next lecture. Let us stop here and we shall discuss about this supernova explosion and the neutrinos coming out from here. Thank you very much.